Finally, we're coming to the end of the journey to find how to get the potential from a particular charge distribution. Because a charge distribution means you don't just have one point charge. We showed in the previous video how to get the potential due to a one-point charge, but in any arbitrary charge distribution, it could have several point charges, and even in a more complicated case, it could have continuous charge distributions. So how would you get the potential when you have many charges? So here in this case, you have charge Q1, Q2, Q3, Q4. You could have many more charges. The distance between charge Q1 and point P where you want to find the potential is R1P. The distance between charge 2 and point P is R2P, and so on. I'm going to give as a result, as a given, and of course, as usual, we'll do the derivation in the next video. You can watch it if you want in detail. But the potential at the point P just turns out to be the sum of the potential due to each charge as if all the other charges don't exist. For instance, V1P is the potential at point P due to charge 1 as if all these charges don't exist. V2P is the potential at point P due to charge 2 as if all the other charges don't exist, and so on. So the problem turns out to be very simple, how to get the total potential at a point. You just add the potentials due to all the charges. And this proof, it relies on the principle of superposition that we know for electric fields. So we'll show this in the next video. If you want to watch it, you can watch it. But this is the final result. And it shows how simple, and shows the reason why the concept of potential is important and why it's a nice way to get the electric field, because when you're getting the potential at a point in space, you're adding numbers. So adding numbers is very easy. The potential due to charge 1 is kq1 over the distance between charge 1 and point P. And then the potential due to charge 2 is kq2 over R2P, and so on. And so getting the total potential just involves adding these numbers. You're not adding vectors, so it's much easier to get the potential than it is to get the electric field. And we can write down the potential as in a summation notation like this if you want. In the next video, we'll show the proof.